34, we're going to use composites to prove that two functions are inverses of each other. Okay, if that's the case, I should be able to place one into the other. So I could composites both ways, and I should end up with x. So let's go this way first. I'm going to take this, and I'm plugging it in here. So I end up with 2 times x minus 3 over 2 plus 3. So I replace the x with that. Now my 2's cancel out here, so I end up with x minus 3 plus 3, and then I end up with x. So that tells me that the composite of f and g ends up being x. Okay, so that checks out. Now we have to do it the other way. So now what we're going to do is take this and plug it in for this. Alright, so I'm going to plug in 2x plus 3 minus 3 over 2 is what I'll end up with when I do the composite the other way, if I go g of x. Alright, and so what happens here is the 3's cancel out. Okay, I get 3 minus 3, so I end up with 2x over 2. That cancels out, and I end up with x. So I end up with this composite ends up being x as well. So that both checks out. So since it works out both ways that they end up at x, they're inverses of each other. Alright, now we're using the same process for number 35. The only difference is here is it's not linear. So it may look a little bit different, but again, we're going to do composites. I'm going to take this, plug it in here. So I end up with a fourth times 4, square root of 4. I'm going to square that. Now when I square this, I end up with 1/4 over 4x. Okay, so 4x times 1/4, I end up, that'll cancel out and end up with x. So that checks out. So when I do the composite like this, I end up with x. Now let's do it the other way as well. Now I'm going to take this and I'm plugging it in over here. Well, I'm going to take the square root of 4 and put in 1/4 x squared for my x value. So it's replacing that. So when I do this, 4's cancel out and I end up with a square root of x squared. Take the square root of this and end up with x. So that checks out. So when I do the composite here of f of x, now on the paper there was some domain restrictions, and that's because you can't have a negative underneath here. But for us right now, we have g is equal to x as well, so that checks out, and they're both inverses. For 36, it asks, we are given a function. It's a rational function, 2 over x plus 3. We're asked what's the domain, what's not included in the domain. What value is not included in the domain of the inverse of the function f of x? It's 2x plus 3. Now here our domain restriction is, we know that we cannot have 0 in the denominator. Because if you have 0 in the denominator, this would make this not undefined. That would be undefined. So x cannot be 0 for this, and so y can't be 3. So the domain can't be 0, and then the range can't be 3. So it asks for the inverse. Well, the inverse, remember, we're going to switch the domain and the range. So y now can't be 0, and x can't be 3. So we switch these. So for the inverse, the domain restriction is x can't be 3. For the function, so for f of x, the function, x can't be 0. Here, for the inverse, x can't be 3. Okay, because we're switching the x and a y. When we do, we're switching the input and the output. Alright, now let's look at question 37. 37, we're given some choices. We're given f of x is equal to 4x minus 2. G of x is equal to x plus 2 over 4. And then we're told the composite is equal to x. So if we took g of x and placed it in there, we end up with x. So that leads us to believe that it is a function. And so we're given some choices that they are inverse functions because it's not equal to 0. Well, that doesn't mean that it's a function. I mean, an inverse. It says they are an inverse function because f of g is equal to x. So B is a possible choice. So B is the answer we're going to go with because they are functions because are inverses of each other because of this. Because when you do the composite, you end up with x. Alright, question 38. Alright, we're given a graph of a decay, okay, with this. Now, so let's look at our domain. Domain would be all real, so we'd go from negative infinity to positive infinity. Okay, then our range, we're going to get closer and closer to 1. I mean, not 1, 0. So y has got to be greater than 0. So that's all positive numbers. Alright, and so for the inverse, remember we're going to switch our domain and range. The input and the output are going to switch. So then our domain would be x has to be greater than 0. So x would have to be all positive numbers, and our range would then be unlimited, or all real numbers. Okay, so let's look at our answer choices here. So this is for the inverse, okay, and this is for our function. Now, if we look at this, it says both domain and range are all real numbers. Well, A couldn't be a choice. This says B, both the domain and the range are a set of all positive real numbers. Well, here, if we look at the function, okay, yes, the positive numbers are included, but we also include the negatives for the range. So that's not the choice. And we read C, the domain is a set of all real numbers. Well, our domain has got to be greater than 0, so that's not a chance. So for this one, we're going to end up with D, because the domain's all positive numbers, and the range is all real numbers. So D would be the answer for this. Hopefully this helps out, and yeah, you can make some sense of this, and you can do well on the benchmark tomorrow.